All right, this will be a presentation on Aryabhata's kuttaka. Aryabhata lived in the 5th and 6th centuries AD in India, and he got started with making math things at a pretty ripe young age. So at age 23, he wrote a work titled the Aryabhatiya, which was actually an astronomical work, but of course, if it was astronomical, it involved a whole bunch of math. It was written in Sanskrit, and it was composed of 121 verses. The first 33 of these verses were purely mathematical. They weren't astronomical, purely mathematical. And in these verses, Aryabhata demonstrates how to find square and cube roots. He finds the sum of arithmetic sequences, which is really fascinating. And he also solved some geometrical problems. And one very notable contribution of his was a method for solving a certain type of system of linear equations, in particular, those of the form where there are just two equations and two variables of the form ax plus b equals n and cy plus d equals n. So the linear equations both have to equal the same thing, but they're just of one variable where a, b, c, and d are given to us. And this system arises from a question that is similar to this. A quantity divided by A leaves a remainder of B, and the same quantity divided by C leaves a remainder of D. What is that quantity? So, sort of in a more one-to-one equation, what this is saying is that our quantity N divided by A gives us some whole number with a remainder of B over A. B is the remainder. And same thing, N divided by C leaves a remainder of D. And again, in these problems, A, B, C, and D were all given to be positive integers, and N was expected to be a positive integer as well. So Aryabhata's method for solving this type of problem he called it the kuttaka, or the pulverizer, which involves reducing the system to a simpler system that could be solved just through trial and error, simple trial and error, a couple of guesses, and you get the answer. So to do this, what Aryabhata did is he set the two equations equal to each other. So ax plus b equals cy plus d. And then he would solve for one of the variables, either x or y. And you have to be careful about which variable you solve for. You can't do it arbitrarily. You actually have to solve for the variable that has the smaller coefficient. So once he would solve for this variable, then he would rewrite that equation in order to remove the fraction. So the way that this would kind of look is if we went through and we solved for x, say, so remember we're going from ax plus b equals cy plus d, and we're solving for x, so we subtract b from both sides, we divide by a, and x is equal to cy plus d minus b all over a. We can break this up as cy over a plus d minus b over a, and then suppose that a goes into c prime times. Then we could break this up further to say that cy over a is equal to c prime y plus ry over a, where r is the remainder of dividing c by a, plus d minus b over a, of course. And then this is kind of the important part, that we then introduce a new variable to remove these fractions. We just say, okay, whatever this ry over a plus d minus b over a, whatever that is, don't worry about it too much. I'm just going to call it w. So he rewrites x to be c prime y plus w. And then he sort of repeats this process until he finds a simple equation that could be solved easily. Again, by easily, I mean literally testing just a couple of values and finding the answer. And then he would work backwards to determine the desired quantity. So here's how that looks. It makes a little bit more sense when you actually just go through a problem rather than talking about it abstractly. So suppose that we have this problem. A quantity divided by 14 leaves a remainder of 9, and that same quantity divided by 51 leaves a remainder of 3. What is the quantity? So to use the kuttaka, we begin by forming our equations, which is 14 ends up being 14x plus 9 equals n, our quantity, and 51y plus 3 equals n. So first we'll set these two equations equal to each other. And because x has the smaller coefficient, I'm going to solve for x. And when I do that, I receive x is equal to 51y minus 6 over 14. 51 divided by 14 is 3 with some remainder. So we could rewrite this expression of x as x equals 3y plus ry, where remember r is the remainder, minus 6 over 14. And then again, removing this remainder technically would be a fraction. So removing the fractions, I just combine the ry minus 6 over 14 into w. So now I have the expression x equals 3y plus w. But note now that I have two different expressions for x. So I have x is equal to 51y minus 6 over 14, and that's also equal to 3y plus w. So what I can do is working with these second two, this sort of second equation here, I can rewrite this again to remove the fraction just by multiplying through by 14, and I get 51y minus 6 equals 42y plus 14w. And now I can go ahead and solve for y. And when I do that, I get y is equal to 14w plus 6 over 9. Again, same thing. I'm going to rewrite this to remove the fraction. So 9 goes into 14 one time. So I end up with y equals w plus u, where u is whatever the remainder is plus this 6/9. And again, I've got two expressions. Y equals 14w plus 6 over 9 is equal to w plus u. This is the new formulation that we just made. If I multiply through by 9, I achieve 14w plus 6 equals 9w plus 9u. And solving for w, I get w is equal to 9u minus 6 over 5. And at this point, this is actually not too difficult of an equation to solve. For people who maybe work with numbers pretty frequently, we might immediately see that if we plug in u equals 4 into here, 36 minus 6 is definitely divisible by 5. So this is a place where I would say that somebody using the kuttaka, they have done it successfully. If we can get to some kind of denominator that's easy to work with, like 2, 5, or maybe even 10, those are pretty easy to work with. Just something that's sort of small and easy to work with. So u equals 4 works in here, and when we plug in u equals 4, we get that w is equal to 6. This requires only testing 4 integers. And when I mean testing integers, I mean start with the smallest integer, so 1, and plug that in. If I plug u equals 1 into here, 9 minus 6 is 3. That's not divisible by 5. So I would increment. I would try u equals 2. That's also not going to work out. U equals 4 is the smallest integer, so in order to find that solution, I would only have to test 4 integers, which is not that bad, considering sort of what we started off with, which was like it was not at all obvious what we could plug in to solve the initial equation. So we've already found a solution to our kuttaka, but I just want to kind of demonstrate really the power of it, that you don't even have to sort of test four values. If you do one more iteration, you only have to test two values. So if we reduce w equals 9u minus 6 over 5, that gets reduced to w equals u plus v. Then we can set these equal to each other. 9u minus 6 over 5 is equal to u plus v. Solve for u. U is equal to 5v plus 6 over 4. And once again, this is not a terrible denominator to work with. 4 is not awful. So if we start testing values of v, if I plug v equals 1 into here, 5 plus 6 is 11, definitely not divisible by 4. If I try v equals 2, 10 plus 6 is 16. That is divisible by 4. So getting down, even just doing one more iteration from the previous one, we only had to test two numbers before we found a solution. So when v equals 2, then u equals 4, which is, of course, what we found on the previous slide. I'm just showing this to demonstrate that we really can simplify these equations down and make it very easy to solve by trial and error. And now that we have our solution to our simplified our simplified equation, it's just a matter of plugging back into our previous equations until we can calculate n. So from v equals 2, we found that u is equal to 4. With u equal to 4, we have w as a formula just based off of u. So plug u into this formula to find w, and when we do that, we find that w is equal to 6. We had an expression of y just in terms of w. If I plug 6 into that, I get y equals 10. And now I'm ready to solve for n. I don't even have to go back and solve for x because I already had n written in terms of y. So now that I have a value for y, I plug that back in, which we had, just to remind you, we had n is equal to 51y plus 3. If I plug in y equals 10 into here, I get 510 plus 3, which is 513. So, and yeah, this first one's pretty easy to see. 513 divided by 51 does leave a remainder of 3. And also, it's true that 513 divided by 14 leaves us a remainder of 6 as required. So the kuttaka has found our initial quantity, which we were able to find really pretty easily just by guessing a couple of values.